today I will teach about UART receiving code. So let's write the code. We will receive data and turn off my keyboard. This line is just including the library stdint.h. And this library mainly focuses on the width of the integers that are type like 8 bits, 16 bit, 32 bit, 64 bit. Here in this code we are going to write about Cortex M4 based Java microcontroller which use register, many register, and their 32-bit size, and their values are stored as integers. So because of that, we are going to use the 32-bit integers that are typed from this stdin library. This is just including the library of Java microcontrollers so that we can use all its functions, objects, whatever. This is just the library of this is just a function of receiving data from the UART data transmission process. Let me explain these functions later on with the flow of the code. This is just a delay functions. Let me explain this with the flow of the code later on. This is the main function. Let's come to this. We will check the variables. C, and here system control. So now using RCGC GPIO, RCGC GPIO, and its levels equivalence to GRX 0 in hexadecimal is this, 3 in hexadecimal is this. So here the system control is using RCGC GPIO and its value is equivalent to 0x03, 0 in hexadecimal is this, and 3 in hexadecimal is this. So this RCGC GPIO is the 32-bit registers of Java microcontroller Cortex M4 bus. This is a 32-bit register, and this register says supply the clock source to any one of the bit from bit 0 to bit D5 of this RCGC GPIO, from bit 0 to bit D5 of this RCGC GPIO to choose a particular port you want. Means something is wrong. This is about port. Choosing. So I have supplied the clock source to bit 0s, so I am choosing the port A, or GPIO A. If I supply the clock source to here, then I am choosing GPIO B, or port B. If I supply here, the clock shows, then I'm choosing port C or GPIO C. If I supply the clock shows here, then I'm choosing GPIO D or port D. If I supply it here, then I'm choosing port E or GPIO E, and this one is port F, GPIO F. Here I'm supplying the clock shows to bit zeros, so I have chosen or GPIO A. Your system control is using the RCGC UART register, and its value is equivalent to 0x01. Now 0 is equivalent to in hexadecimal is this, and 1 in hexadecimal is this. Here the RCGC UART is a 32-bit register of Java microcontroller on Cortex M4 bus microcontroller, and this RCGC UART 32-bit register says supply a clock shows to any one of the bit from bit 0 to bit 7 of this 32-bit registers to choose a particular UART models you prefer. Suppose I'm here supplying the clock shows to the bit zeros of this RCGC UART register, so I have chosen the UART models 0. You supply the clock shows here, you have chosen UART models 1. Here, if you supply the clock shows, then you have chosen UART models 2, and so on. Okay. Here I have chosen UART models 0, so let me initialize it. Here UART models 0 is now using the control register, and control register value is equals to 0. That means all the values, all the bit of this control register 32-bit register is now equals to 0 except all those reserved 1. This is the control UART control registers that control resistors, and this UART enable bit is equals to 0. So UART is now disabled, then all the other functions of all those bits will not operate because UART is now disabled. And disabling UART is necessary for quite some time because we want to set up everything, all the configurations of UART, and after that we will enable the UART. Let me explain this two lines together because this only represents one thing. The baud rate. The baud rate means speed at which the bit is transmitted in the UART data transmission process, or the rate of data flow or bit flow or stream of bit flow in the UART data transmission process. So that's called the baud rate, and this can be calculated using the following formula given below. And the formula is desired baud rate equal to system clock by 16 multiplied by clock tip. This is multiplication symbol and not underscore. This is multiplication symbols. The system clock has a default values of 16 MHz. Yeah, the default system clock value is 16 MHz. The 16 MHz we will put in the system clock, and this become 16 MHz, and the desired baud rate equal to 16 MHz by 16 multiplied by clock tip. This is multiplication symbols. If we cancel this 16 and this 16, we get 1 MHz by clock tip, because this is multiplication symbols. So we will cancel this 16 and this 16, then we get 1 MHz here and clock tip. So it becomes 1 MHz by clock tip. So we will put 9600 as the values of the clock tip. Here, this is only a unit of frequency, so we will not consider this. This is 1, so we will not consider this. This is 9600. So the only main term left is 9600. This is the right hand side of the equation, which we get from this by putting the clock tip value 9600. So this is the right hand side of the equation. This is the left hand side of the equation. So the only main term left in this equation is 9600. So this is the only value left. So here the left hand side says baud rate. So this becomes the values of the baud rate, because this is the only value that is left, the main term. So this is the values of the baud rate. In many books you will find the value of the baud rate 9600, 4800, like that. This megahertz is a higher unit of frequency. Let me reduce it to standard unit of frequency, hertz. This is because in mathematical expressions or calculations, we usually reduce the hierarchy unit to the standard unit. This megahertz is 1000 hertz. So let me write 1000 hertz divided by 9600. This is same 1000 hertz divided by 9600. This expression, what does it say? This expression is saying sending 1000 bits at a baud rate of 9600. Okay, let me consider only sending 1 bit at a baud rate of 9600. So here we will write only 1 bit is sending at a baud rate of 9600. You will find in many books 9600 as the values of the baud rate. What is the meaning of that? Okay, the baud rate value 9600. What is the meaning of that? It means the signal change 9600 times in 1 second. The signal is as you know in a graph, when you draw the signals like sine wave, signal means the wave, sine wave. Everybody knows I think about sine wave. It starts from zeros and then reach the peak, positive peak, and then it again reaches to 0 and then reach the negative peak. Peak means the amplitude, and then again reach the 0. The sine wave. A full wave represents one signal, so that signal changes 9600 times. Then how many signals 9600 signal rate? See how fast it is. Okay, so this baud rate 9600 means signal changes 9600 times in 1 second. You know the meaning of this, right? It's very fast. Okay, so whatever. So here it says 1 by 9600. We'll just write 1 by 9600, and this means signal changes 9600's time, okay, in 1 second. That means per second. That means we can write signal changes 9600's time per second, okay, in 1 second. This one is just that 1 bit, okay. In mathematical calculation, I can bring this to the numerator. Okay, right. So we will write 1 bit into 1 second. So this is 1 bit into 1 second result. Okay, this second I can reduce it to lower, okay, units, as we do always in mathematical calculation, physics calculation, electronics calculations. We will reduce it to microsecond. 1 second is 1000 microsecond. So it becomes 1000 microsecond by 9600. When we divide this 1000 by 9600, we get these values. Okay, and I take the unit microsecond, this one, because this is unitless. It only means number of changes of signal, so it doesn't have any unit. So because of that, I take this unit microseconds from here. Okay, this is integers portion. So this is a times, right? This is microsecond. It is a unit of time, so it represents times. So finally, after calculations, we get regarding sending of 1 bit at a baud rate of 9600 means finally we obtain these values. That means in sending 1 bit, this much of time is needed, because this is regarding rate of data transmissions. That means speed of bit is transmitted. So regarding 1 bit, this much rate of time is required. That means this is the speed of data transmissions. That means after sending 1 bit, we need to wait for this much times. Okay, and then after waiting for this much time, we can send another bit, and we will wait for this much time, and after that we will send another bit like that. So this is the speed of data transmissions or rate of data transmissions. Because if you still don't capture what I mean, this is speed of data transmissions. If I reduce this value, okay, by making this value higher unit of baud rate, like 115200, okay, this is so far the highest value of baud rate, then this denominator will become 115200 means use value. So this will become very small. Okay, so this will divided by this much value divided by 115200 means, you see how this will be a very small value. Then we have to wait for a little time. Then here speed of data transmission is higher, because 1 bit will be sent, and then we will wait for a little time, 1 bit will be sent again. So speed of data transmission is high. But this is average time value. So we will wait for longer times. After sending 1 bit, we will wait for this much longer time after sending 1 bit. Okay, so this is medium speed, right? So this become a speed of data transmissions, like that. Or the rate of data transmissions. Okay, this is the times, but with this times we are going to maintain. Okay, from this time we have to maintain the speed of data transmission, right? Because of that, so this is 104. This is integers value, so I will store in integers baud rate devices register, UART integers baud rate devices register, and this is fractionals value. So I will multiply. This is multiplication symbol and dot underscore, so I will multiply by 64, add 0.5 to it to get the decimals value. So I will store this 11 in the UART fractionals baud rate devices registers. So I will store that 11 in the UART fractionals baud rate devices register. And because of that, I store 104 in the IBRD integers baud rate devices register, and I store 11 in the fractionals baud rate devices register. Okay, in our code. So here 104 in IBRD integers baud rate devices register, 11 in FBRD fractionals baud rate devices register. So what does this mean? This means this is the speed of bit transfers in the UART transmissions medium, or in the transmission process. We have to wait after sending one bit. We have to wait for this much of time, 104 plus 11 microsecond, and then we can send another bit again, and then we have to wait for this much of time, and then we can send another bit again. Okay, so this becomes the speed of data transmit in the UART data transmission process, or in the UART data transmissions medium, right? CC equal to Joule. This is UART is now using the CC register. CC register is about the clock, and its value equals to 0 means is the default system clock. So UART 0 is now using LCRS register. It is the 32-bit register of Diva microcontroller on Cortex M4 bus, and this register's value is equivalent to 0x6 zeros. 6 in hexadecimals is this, and 0 in hexadecimal is this. So here the D3 bit is the stop bit 2, and stop bit 2 is value is 0, so value 0 means use the default value, and the default value of stop bit 2 is use only one stop bit. And here D5, D5 and D6 is set to 1 1. Setting this bit D5 and D6 to 1 1 make it functions call make it to perform a functions called WLAN, and this WLAN full it is what LAN. Let me show you. Yeah, this is UART LCRS registers. This is D5 and D6 bit. This combined form functions WLANs. This WLANs in actual it is word LAN, the full form word LAN, and this perform a functions when D5 and D6 is equal to 1 1. It perform a function, and the function is to use to pick 8 bits data. In making our data frame, this 8 bit will be used. So we have used this is stop bit 2, the D3 bit. Here I'm giving the D3 bit equals to 0, that means stop bit 2 equal to 0, that means 0 means is the default value. The default value of stop bit 2 is to use one stop bit on in making our data frame. So in making our data frame, we will use one stop bit and ith bit and one start bit. The start bit will be added by default. This is UART register 0 is now using a control register and its value is equivalent to 301. 3 in hexadecimal is this, and 0 in hexadecimal is this, and 1 in hexadecimal is this. Okay, so this bit indicates zeros. This is the bit of this control register, UART control register. Let me explain here so that you become more familiar with the register. This is UART control registers that I wrote in the code as controls. So here, the D0 bit, UART enable bit is now set. Set means writing its values 1. That means UART is now enabled as it is set, so you can now use UART in your codes. This GXE bit, G8 bit, is also now set. This is transmit enables bit. Okay, this one, GXE bit, transmit enables bit. Now, okay, we can, since this bit is enables, we can now, transmit data or bit stream or byte using the UART data transmission process to other device. This is RxE bit, receive enable bit, the D9 bit of this UART control register. Since we have set this bit, that means it is now enabled, so we can now receive data or bit stream or byte from UART data transmission process. So now, as UART is enabled, and we can do here now transmit, and also we can receive data from the UART data transmission process. So this is about initializations of UART. So let me initialize GPIOA. I've done initializations of this UART again. So let me initialize this GPIOA. Zero in hexadecimal, 3 in hexadecimal. Let me explain something. This is the pin of GPIOA. Okay. I have chosen, what I'm going to explain now is nothing related to this line. Okay. I have chosen the pin 1 and 2 of this GPIOA. It has 8 pins. Okay, I have chosen the pin numbers 1 and 2 only because I need only 2 pins of the GPIOA, 1 for TXT pins and 1 for RxT pins. Okay, TXT pin is the pins where we transmit all kind of data or bit stream or byte through the UART data transmission process. An RxT pin is the pins where we receive all kind of byte, all kind of bit stream, all kind of data from the UART data transmission process. So I need to get only these 2 pins, RxT and TXT pins. So I choose only 2 pins. 2 pins of this GPIOA. Okay. Now let me explain this line of code. This line of code is not related to what I have just explained about this. Now let me explain this line of codes. This line of code says GPIOA is now using the Dan register and its value is equivalent to 0x03. This 0 in hexadecimal, this 0 in hexadecimal is just this 3 in hexadecimal is this. This Dan register is in 32-bit registers of TIGA microcontroller and Cortex M4 pins. This Dan register says whatever pin you have chosen for this GPIOA made it a digital pin, because everything we are working here is digital, as we are not using any kind of analog functions here. Okay, that's all. Zero in hexadecimal is this. 3 in hexadecimal is this. This line is saying GPIOA is now using AFSL register. AFSL register is another 32-bit registers of Cortex M4 based TIGA microcontroller, and this register AFSL has the values 0x03. 0 in hexadecimal is this, and 3 in hexadecimal is this. And what does it mean? It means this register is saying AFSL register is just saying whatever pin numbers 1 and 2 that you have chosen for this GPIOA port A, that pin numbers 1 and 2 you have chosen, make it, okay, don't make it just remain as simple IO, but make it to work for many other functions like SPI, I2C, UART, timers, etc. Yeah. One in hexadecimal is this. 1 in hexadecimal is this. So this line is saying port A or GPIOA is now using the port control registers, and its value is equivalent to 0x11. 1 in hexadecimal is this, and 1 in hexadecimal is this. So I set bit 0 and bit 4 of this port control 32-bit registers. Setting the bit zeros of the port control registers 32-bit registers will make this pin 1 of port A GPIOA set it as TXT pins. TXT pins is the pins where we transmit all kind of data or byte or bit streams, okay, in the form of bit by bit everything from the UART circuit to the other device through the UART data transmission process. An RSD pin is the pins, setting the bit D4 of this port control registers will make this pin 2 of the GPIOA or port A set this pin 2 as RxD pins. RxD pin is pins where we receive all kind of data or byte or bit stream in the form of bit by bit. We receive all those bit by bits from the UART data transmission process. So this this is about configurations of GPIO pins as digital pins, as UART pins, okay, and this is about configurations of GPIO pins as JXT pins and RXT pins. All these configurations above, again, all this setup above takes at least 1 millisecond delay. So I will just call the delay functions. What time this gives 1 millisecond delay if we call it one time. I haven't write this function still, so let me write the functions. Board delay ls and so I just take two variables and write after for loop I equal to 0, I less than 10, I plus and then G equal to 0, G less than 3, 1, 0, G plus. Okay, so what is this is the delay functions. We're just taking two variables. Here this is the outer for loop, I equal to 0, I less than n, and here 1 pass through the n, so n value is 1, 0 less than 1, that's true, the condition is true. After this the I is increment from 0 to 1. As this condition is true, this line is executed, and after this it came to this line. This line is j equals to 0 and 0 less than 3180, that's true, and after that j is increment. As this condition is true, this line is execute. Okay, so like that, the next time the j is 1, as this one is already increment last time, so 1 is less than 3180, as this condition is true, this line is execute again. So this j until it becomes 3179, this line will execute. That means since j start from 0, it will execute 3180 times. But this one will execute only one time because we put the value of n 1. That's because we call these functions one time, and so this line will be executed one times. So that like that, and this 3180's time is put this value so that the whole functions take at least 1 milliseconds to execute. We calculate the time of executing this, we calculate the time of executing this, we calculate the time of executing this, and after that we put these values so that at least the whole functions took time 1 millisecond delay. So because of that we close one time so that we get only 1 millisecond delay. So because of that, as all this above setup took 1 millisecond delay. So that's it. And let me write the sample. Here we are receiving. So let me store the receive data like this. So as I haven't write these receive functions, let me just explain it. So from the UART data transmission process, we are receiving some kind of data. As we have said everything, the UART GPIO above, let me write these functions. What is functions? These are just a simple functions. Function, what happened is, let's take the variable c, okay, to store the data we are going to receive. So here, this is just very simple function. Listen carefully again. If you listen, then it becomes more easy. So, this line, the UART 0 is now using the FR register, the flag register, UART flag register, and this flag register value is equivalent to 0x10. 1 in hexadecimal is this, and 0 in hexadecimal is this. So this line again just representing this bit, D4 bit. Because only this bit is set, means its value is 0. So okay, the rest of the bit is not set, only this value is set. That means it means only this bit. Okay, we are going to consider. So what this bit is? This bit is, okay, UART. The name of this bit is receive flip-flop empty flag. So let me tell you about the receive flip-flop empty flag. So this is G4 bit receive flip-flop empty flag of this UART flag registers. So everything here will be on the flag because this is UART flag register, UART FR register. So let me tell you about the receive flip-flop empty flag, the D4 bit of this UART flag registers. Suppose if you receive a byte from the UART data transmission process, it will be first placed in the receive buffer. Okay, RECEIPET. This W should be removed. It should be receive buffer. So the byte will be here first, here receive in the receive buffers, and should say that the start bit comes first, and after the start bit the ith bit comes, and after this ith bit the start bit comes. So the start bit comes finally in the receive buffer. As soon as the start bit is came in the receive buffer, the UART circuitry discard this start bit and also discarded this start bit and put only 8-bit data in the data register. Okay, and after the data has been stored in the data register, only that 8-bit, after discarding the stop and start bit, this receive flip-flop empty flag is set by putting its values 0. Let me tell you again. When a byte has been received from the UART data transmission process, it is first placed in the receive buffer in such a way that the start bit comes first in the receive buffer, and after the start bit comes the ith bit data, and after the ith bit came the stop bit, and finally store all of them in the receive buffer. When the stop bit is stored in the receive buffer, this UART circuitry then discard the start bit and the stop bit also discarded, and only the ith bit data it took from this receive buffer and placed in the data register. Okay, after this receive flip-flop empty flag is set by putting its values to 0. So So this UART 0 is now using the FR register, flag register, and its values equivalent to 0x 10. That means 1 in hexadecimal is this, and 0 in hexadecimal is this, and so this line, this line represent only the receive flip-flop empty flag, and this will be set when its value is equivalent to 0. But here it is not 0, but the while here says it is not equal to 0, but it will be 0 after some time. It means it is not equal to 0, but it will be 0 after some time, means wait for some time and it will be equal to 0. That means we are waiting, right? And what we are waiting is data to be received in the buffer. The start bit will come 8 bit after the start bit, and will come the stop bit after the 8 bit. This will be stored in the buffer, and your circuitry discard the start bit and also discarded the stop bit, and only 8 bit will be stored in the data register. This takes some time. That's why we are waiting. When the data is finally stored in the data register, this receive flip-flop flag will be set by putting its values 0. So at that time, this will be equal to 0, and the receive flip-flop empty flag will be set. That means when this flag will be set, that the data is already in the DR data registers, right? The data is already in the DR register, because here it says when the data is in the data register, this receive flip-flop empty flag is set by putting its value 0. So here the flag is set after some time. That means data is in the DR register. And so we have received data in the data register, and then let me store that data in the variable C, and let me just return that data stored in the C to our main code. So it returns this data we receive from the data UART data transmission process to our main code when we call that functions in our main code inside the for loop. So we call that functions and it returns data, so we store that data in the variable C. Suppose if the data received is A has ASIC value of 41, 4 in hexadecimal, this 1 in hexadecimal, this. So this will be framed between the start bit and stop bit, and will come to the receive buffer. The start bit will come first in the receive buffer, and after waiting for how much time? As I have told already, after waiting for 104 plus 11 microsecond, we have fixed the rate of data transmissions. After 1 bit, we have to wait for 104 plus 11 microsecond rate in this two line. So first start bit will come, after that we have to wait for 104 plus 11 microsecond, and then the LSB will come and wait for 104 plus 11 microsecond. After that the next bit will come. And so like that it will be stored in the buffer, receive buffer, and then this UART circuitry will discard the start and the stop bit, and finally this data will be stored in the data register. So that's the way we will receive data through the UART data transmission process. Thank you all for this session.